Okay, recording is going. All right, good to see all of you. Thank you for coming. At least a couple people that are here, and if you're joining this on YouTube later, thanks for watching, and good luck today or tomorrow, whenever you're taking the test. So what we're going to do here is we're just going to go through a couple of the practice problems, just kind of in open format here. Probably pick like maybe one from each section or two if people have specific questions that they want to go over for some of the practice problems. So if you do have a question for those people that are here, you can go ahead and ask in the chat if you want, and that'll sort of pop up on my screen, okay? All right, so let's just get right into it. I think in the first section, the introductory stress topics, we've got, kind of a wide range of things going on there. You've got shear, you've got bearing stress, you've got axial stress. I think maybe we'll do two from this section just because there's a couple of different kind of general ideas here. So we'll kind of start easy and work our way to the more sort of difficult ideas. So maybe we can just start with number one here. I'll just pull it in, and maybe we can just go through this one relatively quickly. All right, so fortunately on the computer here, I can just pull it in just like that. Isn't that nice? So we're given this kind of like linkage assembly. It's got 5 kilonewtons of load, and we've got two shafts with different diameters, 30 millimeters and 40 millimeters. And we've got a pin connecting. It's got 25 millimeters, and that pin is in double shear. So remember what that means is that you've got one force one way and then two forces kind of pulling it the other way. So the larger shaft has sort of two forces pulling on the pin in one way, and the smaller shaft has one force pulling the other way. So it asks us for average normal stress in each rod and the average shear stress in pin at A. So let's go ahead and do the normal in 40 millimeter rod. I think this is going to be pretty straight ahead here. Where's my scroll? There we go, my scroll wheel. All right, so remember our normal stress. This is sort of the most basic equation that we have in class, is just your load divided by your cross-sectional area. So for the 40 millimeter shaft, we just basically make a cut through that shaft, and we're going to have a load here, just 5 kilonewtons contained in that shaft, divided by the cross-sectional area, which looks something like pi times the radius squared. In this case, 40 millimeters is going to be 0.02 meters squared. Do the math here, 3.98 MPa. No problem. Getting on with it. You can similarly do the same thing in the 50 millimeter rod. So we're going to have something like, again, same idea. Normal stress looks something like P on A. The 50 millimeter rod here, we have the same load. It's 50 kilonewtons. And then our cross-sectional area is just slightly different. Pi times the radius, 0.025 meters squared. This will get me a slightly, oh, sorry. Did I goof this? Oh, sorry, 30 millimeter rod. Why did I write 50? It says 50 in the solution manual. Whoops, 30. So in the smaller rod, it's 30 millimeters. So, sorry, here we do this calculation. We're going to have more stress, 7.07 MPa. Now, lastly, the tricky bit here is this pin that's in the middle. Like I mentioned, it's in double shear. So pin. And so here we're in double shear, and remember what that means. So if I'm looking at the pin like this, and I think about what's actually happening here, well, it's got like one mechanism that's kind of like pulling it this way with 5 kilonewtons, and then it has sort of this other side that's sort of pulling on it with 2.5 on each side. Okay, so this is what it means to be in double shear. So if we actually look at what the pin looks like with those sort of supports removed, it's going to look like 5 kilonewtons, 2.5, and 2.5. So the idea here then is if we make some cut in that pin, sort of in that general location, we're going to see with that free body diagram is this 2.5 kilonewtons here. And the internal shear force that has to balance that is going to be 2.5 kilonewtons. So the shear stress that's going to act here is that 2.5 kilonewtons acting on that face, right? So it's 2.5 kilonewtons, that shear load, divided by the cross-sectional area of that pin in that location. So the double or single shear can be a bit tricky, so watch out for that on the test, okay? So here we have a shear stress, same idea of P on A, where here the load that's in the cross-section is this 2.5 kilonewtons if we actually look inside the cross-section at the point of interest. So here we have 2.5 kilonewtons over our cross-sectional area. The pin is 25 millimeters in diameter, so pi times the radius, 0.0125 meters squared. Do a little math here, and it's 5.1 MPa. Questions on that? It's kind of the very basics of this class. So far, so good?
Professor, can you do force over 2 times A for that one?
You could do the single force 5 kilonewtons over 2 times the area. Same idea.
Okay, thanks.
The way that free body diagram would look is you would make both of these cuts. So you would have both of these guys that looked like that. And then your object would actually look like this. Where you'd have that 5 kilonewtons downwards, and then you'd have this guy and this guy. So those two shear forces together must be 5. This guy and this guy together must be 5. And now you have twice the area that you're acting on. If you want to think of it that way, that's F over 2 times A. Hopefully that's clear. You're going to get the same answer either way. Okay. Any other questions on that one? All right, let's slide on to number 2 really quick. Take a look at number 2. Again, number 2 is kind of like a bread and butter type problem. Wouldn't be unusual to see a problem like that on the test. Just saying. Where we have this kind of scarf splice on this wood board here. Something that looks a bit like this. Let's see if I can blow this up just a little bit for those that are in the back row. That's funny because we're on computers. Okay. Okay, so here we go. We've got 200 pounds in tension for this board. And the question is, what is the shear and normal stresses on the plane AA? All right, so the shear and the normal stresses on that sort of inclined face. All right. So in this case, you want to think about the free body diagram and sort of cutting this thing. And when you do that, you're going to have this very steep angle here, and this very steep incline. So here we have the 200 pounds. And I want to think about sort of the equilibrium must be maintained, meaning that I kind of have to have the same sort of resultant force inside this cross section sort of acting in this general direction, sort of equal to 200 pounds more or less. Okay, and so this is going to be some combination of some normal force coming directly off of that cut plane and some shear force that's acting across that plane. So the easiest way for me to kind of handle this is I think about, all right, my shear is parallel to the plane, so it's going to look something like that. And then my normal force is coming right off the surface. So here, this is like a normal force, Fn. Here, this is my shear force, Fv or Fs, however you want to write it, looking something like that, right? So we got to make sure that we're kind of clear with our angles and maintaining our sanity for our angles. In this case, the 20-degree angle was given. So this here, maybe I'll do it in a different color. This angle here is the angle 20 degrees. So that means that this angle here is also 20 degrees, just like that. And in our class, we sort of derived some equations for what the load and the change in area is given these sort of splices. And when we did the derivation in class, we did everything with respect to the vertical. So what I mean by that is, when we derive things in class, And we typically make cuts that look like this. For our derivation, with our, sort of splice cut that we've made here, we used this angle as the angle to define everything. This is the angle theta. And so you may think of this other complement to theta as the angle gamma, where gamma is obviously 9d minus theta. That's one way to sort of like think about this particular problem, right? So if we define based on the angle with the vertical, we know from class that we have something like the normal force is equal to this value P, where we call this 200 pounds without P, times the cosine of that angle theta. Okay. We said then that the shear force was going to be P times the sine of theta. And in the case where you don't want to define from the vertical using the angle theta, but instead you want to define from the horizontal, which is actually what we have here, this 20 degrees, then maybe you want to think about writing this as P sine gamma and P cosine gamma. If you want to think about shear force and normal force in that way, you could use the angle with the horizontal instead of the vertical and use this sort of derivation. I would say just try to like maybe remember one, whatever you're better with or more comfortable with, and make sure that you just on the exam use that angle however you're sort of comfortable with. Okay. In this particular case, since we're given the 20-degree angle, I'm going to roll with these guys more or less and be on my way. One other thing that we need to note here is that we have a new area. And in class, we sort of showed that that new area, I'll call it A theta, the area that's formed after we cut at that angle theta, is going to be, in our case, the original cross-sectional area A divided by cosine theta, or could also be thought of as A divided by the sine of gamma, where gamma is that complementary angle with the horizontal, instead of theta, which is the angle with the vertical. However you want to do it, however you want to think about it. Hopefully I'm not confusing you in the final hour here, but that's what's going to happen. In this problem, we are rolling with these general ideas here, those particular guys. Okay. So looks like I do have a notification. Are we going to do most of the problems or only specific ones? Oh, sorry, I just saw your comment, Yusuf. Not most of the problems, just maybe a couple from each section. So if you want to suggest some that you would like to see, go ahead and I'll make sure to do those, okay? So we're asked for the normal stress and the shear stress on the inclined plane. So sort of the normal stress on the inclined plane, if we want to say the normal stress at the angle theta, this is going to be that normal stress Fn divided by the modified area, which is A theta. Here, the normal force is going to be P cosine theta. So here, this is 200, or sorry, we're going to use the sine gamma. This is going to be 200 pounds times the sine of 20 over the modified area. We were given a cross-sectional area of 2 by 4. So here's 2 inches times 4 inches. And this area is modified by the sine of 20, since we're taking this 20-degree angle, which is the angle with the horizontal. All this together, the normal stress on this sort of inclined plane, 2.9 psi. Similar concepts and ideas for the shear on that plane. It's going to be that shear force, FV, over the modified area, A theta. So in this case, the shear force will use the cosine of 20, because again, we're kind of running with this equation. We're using sort of that complementary horizontal angle in this case. So here we're going to have 200 pounds times sine of 20 over, sorry, cosine 20. Over that 2 by 4 divided by, again, we need to modify the cross-sectional area, using the sine of 20. All this together, you punch it in, and it's 8.0 psi. How are we feeling about this? Thumbs up, thumbs down, sad face, happy face. Looks like Yusuf wants number 7. Okay, we will do number 7. Let's go some of the sections at a time, though. Maybe we'll pick one out of the axial load, like one of the easier. Let's do the stress strain curve. Yeah. Stress strain curve is going to be somewhat important too. Let's just review those concepts from stress strain pretty quick. Reading a stress strain curve and understanding a stress strain curve is just like such an important fundamental thing you need to take away from this class. So I value it at quite high importance, meaning it might show up on Friday. Okay. So let's go ahead and look at number 6. And we've got this interesting looking stress strain curve. You've not seen something exactly like this before, but it's got this like 2 scale again, right? Where this sort of lower curve would use the lower scale because it's trying to blow up that very stout, short linear region on the front end of the test. And then here, this larger curve is sort of trying to show you what's happening more on the back end of the test, okay? So this is just sort of a very blown up version of like the very skinny sort of low displacement curve, like in this region of the larger curve. So keep that in mind. Okay, so we have a sample, original diameter was 0.5 inches. And we had an original gauge length of 2 inches. And in this particular problem, we want the elastic modulus E, which is the elastic modulus. We want the load on the specimen that causes yielding. So I'll label that as P capital Y, load at yield. And maybe let's pluck a couple other things on here just for fun. Let's say what's the ultimate stress and what's the breaking strain. Okay, so this is modulus, load at yield, ultimate stress, and strain at break. Just so we can pluck a couple extra things off here. All right, so let's go ahead and do this. Let's first start with the elastic modulus. If we have just sort of this one-dimensional loading, which is typically what we have with the sort of tension tests from like a standard dog bone type specimen, we're just going to have loading in this singular dimension. So when you have this one-dimensional loading case, it sort of simplifies the equation. We'll use Hooke's law, which says here that stress is modulus times strain, or if you rearrange this, the elastic modulus is simply the one-dimensional stress over the strain. So this is basically just the slope of the curve. Just like rise over run on this curve over here, right? This is going to be your elastic modulus. So you can really pick any 2 points really on the graph that you want. Probably the easiest way to go about it is, you know, make one of your 2 points 0 and then some other point on the curve, and then just, you know, sort of do the difference there, right? Okay, so I think probably the easiest is to just take this 40 KSI, because this is right on the 0.001. Remember, when you're looking at the smaller curve, you have to take the lower scale here, okay? So we'll pluck off that point. Here we have 40 KSI over the strain at that location. Be careful with the units here. So in this case, we have inches per inch, which is a direct strain measurement. You could see things like microstrain on this axis, remember, which is like everything times 10 to the 6th. You could see something like a percentage where everything is like 100 times larger. So just be a little bit mindful about like some of the units sometimes on the strain can trip you up, but okay. So here we're just using strain units directly. Inches per inch is more or less unitless, so we're at the correct strain units here to calculate the modulus. So we'll just take this 0.001 directly. And so this is just a change from KSI to MSI. So this is just 40 MSI. All right, no problem. Next, we want the load at yield. So for the load at yield, we need the stress at yield. Okay, so we need the stress at yield, and though we're not explicitly told this, we need to use a method that we've talked about in class to sort of calculate this yield stress. And the method that we talked about in class is the 0.2% offset method. All right, so 0.2%, again, be mindful of the units of strain. So 0.2% is 0.002, right? So if the strain units are inches per inch or unitless in some way, then we want to start our offset method at 0.002, not 0.2. Again, be very careful about that. So let's remind ourselves what that 0.2% offset method is. So we're going to start at an x value of 0.002 and a y value of 0. So here's my 0.002 right here. So that's where I'm going to start. And I want to draw a line that is parallel to this elastic modulus line until it runs into my stress strain curve. So it's going to look something roughly like this. Okay, and this has the same slope as the elastic modulus that we calculated. So I'm running into my graph like right around this particular location, which I might call, I guess in the solution manual, I called it 43 KSI. Okay. So here we'll get a yield stress 43 KSI. Using the yield stress, I can then use the cross-sectional area to get the load at yield. So then we'll use that the yield stress is the load at yield divided by the cross-sectional area, rearrange. We have load at yield is going to be the stress at yield multiplied by the cross-sectional area. We're told originally that the specimen has a diameter of 0.5 inches. So here, could rearrange this to be 43 KSI multiplied by the cross-sectional area, which is pi times the radius squared, pi times 0.25 inches squared. And this will give us a load at yield here of 8.4 kips. And remember, kips is 1,000 pounds. This is 8,400 pounds. Okay, so a little like hidden step here, understanding what the load at yield is versus the stress at yield, making sure you understand that 0.2% offset method, just understanding how to run a stress strain curve and understand and read it well. Okay. Last thing, ultimate stress and strain at break. This is just the highest stress that it can handle. We go back to our curve, just look at the peak of the curve. Somewhere up here, let's maybe call it, I don't know, 76, 77, something like that. $76-ish KSI. Solid. Lastly, strain at break. Again, this is just plucking off the point on the stress strain curve where sample breaks. So you have to be able to identify in the stress strain curve what that is. So remember that the stress strain curve is just basically we're pulling on the sample, pull until it sort of turns over and starts to break. So here's the breaking point for my particular sample. I'm going to track my way down here, somewhere around there, and I'm going to use the upper scale here, like I said, because we're looking at the larger stress strain curve, the full curve. So maybe 0.26-ish is probably reasonable. And no units required here. It's 0.26 strain, inches per inch if you want, but this is unitless. If you wanted to represent this in percent, you could do 26%. Kind of interesting to think about that, right? The sample got 26% longer. It's kind of interesting to sort of like think about it that way. So when it failed, it was 26% longer than it was when it first started. It's kind of crazy to think about a metal like maybe doing that. Questions on the stress strain curve before we move on. And we'll do number 7 here for Yusuf. Okay, our journey continues. Number 7, we've got a bit of one of these problems that has what we call a constitutive relationship, right? It's a relationship that's sort of dependent on geometry. And sometimes you just have to deal with this static indeterminate situation and investigate what's going on here. So let me copy this over and we'll sort of talk about this. We've had problems, a couple of problems now, similar to this. I think we did one in class and we had one for the homework. Both kind of use like one member that was completely rigid. In this case, we have a similar idea. Get out of here. This time, member ABC is completely rigid, and B, D, and C, E are not. Okay, so let's see if I can actually copy over the problem statement as well. Will help keep things moving smoothly. So here we have link BD. It's made of brass with a modulus of 105 GPa, cross-sectional area of 240 square millimeters. That's that piece on the top here. And we have another non-rigid link EC made of aluminum, 72 GPa, cross-sectional area 300 millimeters squared. They support the rigid member ABC, so we want to determine the maximum forcing be applied at A if the deflection of A is not to exceed 0.35 millimeters. Okay, so this comes up commonly where you have like a rigid member that looks like this or something you're going to approximate as rigid. And you know that if it's all right, perfectly horizontal at the beginning, and then we have some load that's applied, it's still going to stay in a horizontal, or sorry, in a perfectly linear fashion, but it's just going to like pivot and tilt a little bit. So you're probably thinking to yourself some linear equations where we're looking at deflections of various points and sort of trying to keep all that together. All right, so how can we handle that? Well, we know the deflection at A is not to exceed 0.35 millimeters. Okay. So I'm going to load this on this particular side, and what's going to happen? Well, you could probably imagine in your head that this side's probably going to go down and this side's probably going to go up, or maybe this side goes down or something like that. You know, not sure. But let's just go ahead and run with the idea that A is definitely going to move down, B is probably going to move down, and let's just say C is going to move up. So maybe just go with some sketch of what's going to happen. Is that originally you have some original state of A, B, C. Here's A, here's B, and way over here is C. Okay. And then once you load this thing, it's going to come to a new configuration. I'm going to really maybe exaggerate this, but it's going to have a new configuration that's maybe going to look something like this, okay? And we're going to have some downward deflection here, which we're calling delta A, or downward deflection. We know what that value is, okay? It's going to be 0.35 millimeters, or assigning that, okay? There's probably going to be some downward deflection of B. Let's call it delta B. And then we're going to assume some upward deflection of C. Let's just call it delta C for now, and let's let the math take us where it needs to go, okay? So this is kind of the general setup that you want to have. And we're looking for, like, what is the equation of this line? All right. Well, I have point A, and I know sort of the coordinates of that. According to this, it's at x location 0, where if this is kind of like an xy coordinate system. And y coordinate negative 0.35 millimeters. That's like the max I can allow, right? Okay, that's where it goes. What about point B? Well, point B is going to go to some displacement of B. Let's call it delta B. Sorry, that's not its x-coordinate. Its x-coordinate is given in the problem, 125 millimeters. So let's call it 0.125 meters, or maybe you call it 125 millimeters, whatever you want to do. I guess I stuck with millimeters in the solution, so let's go with 125 millimeters. And some deflection of B. Maybe you call it negative delta B, or let's just roll with delta B at the moment for its particular location. It's going to deflect downwards. C, it's going to go to 350 millimeters. And then its final location, let's just call it delta C, and we'll let the math kind of take us there, right? So then the question is, how do we establish like delta B and delta C so that we can sort of create our equation for our line and determine what the final positions of all of these things generally are, okay? That's the strategy here. And we know from what we've discussed in class that the deflection down of B and the deflection down or up at C, whatever it's going to end up being, is going to be governed by sort of the forces inside of these links here that are non-rigid, CE and DB, okay? So we've got equations that we've used in class that help us determine what those deflections are going to be. And so here we need sort of the deflection of B and the deflection of C, and we'll use this idea of PL over EA. So this derivation of what is the displacement or deflection of these beams given these properties and the loads that are currently on them. Right? So I need to know what those loads are, and I need to know what they are in terms of what load I have applied at A, which is that load P. Okay, so I need to do some statics here, sadly, to sort of understand what the loads are in members DB and members CE in terms of what I'm applying at A. I need to do some statics here to sort of figure that out. Okay. Need statics. Find the force at B and the force at C. Okay. In terms of P. Where P is what I'm applying to the bar. All right. Okay, that means free body diagrams. Specifically of that long slender, or that middle bar there, ABC. Easy as 1, 2, 3. Right? Right. Did I miss a question? I think I might have missed a question. After 7, can we do 10 and 11? Sure. So let's go back to ABC. Here's our member ABC. Pretty straight ahead here. We're going to load this guy with an unknown amount P. Remember, we're not dictating this problem we're trying to solve for that unknown load P. We need to make sure that it doesn't deflect point A down that 0.35 millimeters. Okay, so here we have what's going to be the force at B. And here we have, I don't know if it's going to be up or down, but let's just say the force at C. All right, so let's go ahead and work through this. Statics analysis. Some of the moments. Here I'll pick the moments about B equals 0. I think that's quite easy. Here's point B, because we kind of know all the lengths between, A and B and C. So life is easy if we just generally do that. So moment about B, this load P is going to create for us a positive moment. So here we're going to have 125 millimeters, just as a reminder, this is 120 millimeters between these two guys. So 125 millimeters times P, positive moment contribution, minus, I'm going to get a negative contribution from this FC, and that is 225 millimeters away. So minus
I
2.
had a quick question about FB and FC.
Go ahead.
So is it because members BD and CE are two force members that
Yep.
we ignore the reactions at point D and point E?
Right. So because BD and CE are two force members, you can draw the free body diagram of ABC just with the forces and the directions of the members. Right.
Okay.
So remember, in
And
two force members, the load always has to be moving through the line between the 2 points where that two force member is connected.
okay.
Clear on that?
Yeah, and then two force members are specifically members that have the forces acting on only 2 points within the member? Or what was the definition of two force member again?
Yeah, so a two force member is exactly that. One where there's only two loads, 2 points of application of load on a body. So if we just have a really quick aside here, you could have, again, your mechanics potato, whatever it is. You have a point over here and a point over here. If those are the only 2 points on the structure where there is load, let's say that, I don't know, this guy is got some line of action here, then the only way that this thing can transfer load is either with forces that are equal and opposite this way, if it's in static equilibrium, by the way, or forces that are equal and opposite this way. That's the only possibility to maintain moment equilibrium and maintain some of the forces in X and Y equal to 0. If you had any other arrangement of the forces, then there would not be any equilibrium. Hopefully that's
So the
clear.
forces acting upon the object have to be within the same line of action.
It's the line between the 2 points where the forces are applied.
That is the line of action. Okay.
Yeah, so one example that trips people up sometimes is like an L bracket that looks like this. Okay, so let's say I have a point over here and a point over here, and both of them are pinned. Okay, this one confuses people a lot, but you could draw the free body diagram of this system where that's your line of action, like between those 2 pins, and the force you could draw this way and this way along that line of action. It's still a 2 force member. There's still only 2 points on that structure where load is applied. And you just have to make sure that you draw them not along sort of like the shaft like this, because that's not accurate. You have to draw them along the line of action between the 2 points where the forces are applied. Is that clear?
Yes, thank you.
All right, cool. I got to run and get my charger really quick for my laptop. 1 second. Okay, I'm back. Sorry about that. Didn't want to die halfway through there. That would be not so good. Okay, so back to the problem. So we had done the sum of the moments about that central point at point B. And using this, you can write the force at C in terms of the load P, which is going to be helpful for us. So here, I'm going to write it as some percentage, right, or some multiplier, which you can determine from the algebra here 0.556 times P. Keeping the train rolling, we can do some of the forces y equals 0. Here we have P downwards, we have FB upwards, and we have C downwards. So using this, you could determine that the force that's acting at B upwards is going to be 1.556 times P. Now, it's important to write these forces in terms of P because ultimately that's what we're looking for. So if you can sort of whittle this down and write those forces in terms of P later in the problem, your life's going to be a lot easier because the only variable that's going to show up is that variable P. Okay, so now we've got FC, we've got FB. Let's go back to our deflection equations. So deflections. So the deflection at B is going to be that force B times the length of member BD over the modulus in the area of that member BD. I'll just kind of put some subscripts on here to make sure that that's kind of perfectly clear. So this member BD was made out of brass. So it told us in the problem statement some of the information about that particular member. So we can include that here. We have FB, I'm going to write it in terms of P. This is 1.556 times P. The length of member BD given in the problem is 225 millimeters. So I'm going to write this as 0.225 meters. And then this is divided by the modulus of the brass, 105 GPa, just like all of your GPAs. And then the cross-sectional area of this particular member. It's given to us in millimeters squared. I'm going to write it in meters squared. This is going to be 240 times 10 to the negative 6th meters squared. Okay. Put this all together, and you're going to have some coefficient in front of the variable P. So 0.0139 times P. Okay, now the question is, what's happening to the units? Because this can be a little confusing. All right, we've got gigapascals here, which is kind of like a 10 to the 9th sort of thing going on. All right, we've got meters, we've got meters squared. Remember that this is going to be something like 10 to the 9th newtons per meter squared. Okay, so maybe you want to write this leading coefficient in such a way that your deflection will be in meters and your load here will be in newtons. Okay, sure, go about doing that. Set yourself here, P is in newtons, cancel all these things out, retain all the units properly, so on, so on, so on. Okay, in the solution that I've made up, maybe you've looked at this, but I've made some calculation here so that my coefficient is relatively clean, 0.0139. If you wanted to retain standard newtons where this load P is in newtons and this deflection is in meters, you would have a very, very small coefficient here. It'd be, you know, it'd be probably a factor of a million difference. So 0.00000000139. I just don't love that. I want to work with a little bit clearer numbers. So what I've done here is I've sort of assumed that P is in kilonewtons. That gets rid of a factor of 10. And I've also assumed that the deflection that we're going to calculate will be resultant in millimeters, not in meters. So that is also getting rid of a factor of 1,000. So I've written this for P in kilonewtons and displacement in millimeters. Hopefully that makes sense. If not, put your units in that are standard and retain this coefficient, which is going to be a different factor. a couple, it's going to have a different decimal point. The decimal point will move. Okay, same idea here with what's going on at point C. So here we have FC times LCE all over the modulus times the area of that member CE. FC 0.556 times P. And here, this guy is 150 millimeters, so 0.150 meters. All this over the modulus of that member CE. We were told that that member CE was made out of aluminum. That has 72 GPa. Its cross-sectional area, we were told, was 300 square millimeters. So I'm going to put this in as 300 times 10 to the negative 6 meters squared. It's a conversion from millimeters squared to meters squared. Work through this, you're going to have 0.00386 times P. Again, P is in kilonewtons, and displacement here is in millimeters. Okay, now we did have some directionality for the forces when we originally drew them, so we've got to be sure that we're clear on what's happening, is that this displacement is down, and this displacement is up. The reason why that is because we originally showed on the free body diagram that the force at B is up and the force at C is down. So what that means is, by equal and opposite forces, the link at B, if I were to just think about what the link looks like, has to have an equal and opposite sort of force down at the bottom. So this link is going to be in tension, meaning it's going to get longer, and point B is going to move downward. Similar idea with what's going on at C is that if I think about equal and opposite forces for the link at C, I have link at C here, looking something like that, meaning that that link is going to be in compression and point C is going to move. Sorry, this link is going to also be in tension and point C is also going to move upwards. All right, so both of these links are getting longer. C is moving upwards, B is moving downwards. That's important because if we go back to our figure way up here, when we thought about defining what this line looks like, we did actually draw this correctly. So we can sort of leave that alone. We've got that working for us correctly.
I thought it was the opposite. I thought that B was moving downwards and C was moving upwards.
Yeah, did I not say that?
Oh, I don't know.
This figure here is correct. B is moving downwards.
Okay.
And C is moving upwards.
Okay.
Right. It looks a little weird because the force at B is pointing up, yet the resulting point B is moving down. And that's again because you want to think about how this link is responding, not how this force on this particular member is acting. It's a bit of a strange one. But okay, that's the resulting situation. Okay, so well, now what? All right, well, we have the displacements of B and C in terms of this force P that's been applied. So what that means is we have like multiple points on a line now. So back to line. Is that we had sort of our original condition, and now we have our modified positions, right? Okay, so point A, like we said before, had a coordinate which is 0, negative 0.35 millimeters. Wonderful. Point B has coordinates which are an x-coordinate of 125 millimeters, so 125 millimeters if you like, and it is moving down in amount negative 0.0139 p. So now you see why it was important for me to define that this particular load will be defined in millimeters. So when I move up to this particular situation here, I did a bit of a unit conversion to make sure that that leading coefficient, 0.0139, will give me a deflection that's in millimeters. Lastly, point C, this is at this sort of far out x coordinate, which is 125 plus 225. It's going to be 350 millimeters. And this is actually up. So here we have just a positive 0.00386 P for our resultant. So now we kind of just have to work through the equations of a line. I think at this point, the mechanics and the statics are pretty well settled. We've talked about the free body diagram, shown sort of how to handle this problem in general. If you want to see the rest of the solution, there's some sort of geometry there for how to do the calculation of a line, basically finding the slope between those 2 points, calculating P, being on your way.
The last
You got-
question that I had about this problem was I kept my displacement values, the displacement of B and C, in standard units being meters and newtons. So
Yep.
I got the really small numbers.
Yeah.
And when I tried to solve for the equation of a line, y2 minus y1 over x2 minus x1, I was getting weird values for the slope.
Were you using millimeters here? Because if you want to do that, you'll have to convert this to meters.
Yeah, that was in meters as well.
Okay. As long as everything is like clean, all the units are working out, it should work okay. You would end up with, so you have 0.0000139 P here.
For B, it's negative 1.388 times 10 to the negative 8.
Yeah. Okay, so you're off by a factor of 1,000 compared to what I have. But I also have P in kilonewtons. So yeah, okay. It's off by a factor of 1,000,000 because my P I'm working with in kilonewtons.
Mhm.
So I agree that times 10 to the negative 8 should be correct for you. So maybe it's just a problem with the calculation of the slope and et cetera. You'll also have to remind yourself that you probably want to work with this in meters then, these guys.
Mhm. Yeah, those are all in meters as well.
Okay.
Let me run it one more time.
Yeah. You have to kind of check it on your own time. If you want to come by maybe in the morning, I can take a look.
Sounds good.
Okay. All right. So there's a bit of math here, but you can get to an answer of that load needs to be 14.7 kilonewtons. And that's your max value to get to that displacement of 0.35 millimeters at A. All right. Thank you for waiting, Kyle. I think we should maybe move on to the last bits, specifically 10 and 11 Kyle wants to see. Any other questions on this one before we kind of put a cap on it? All right, let's take a look at number 10.
Professor,
Sure.
that question that we just did,
Mhm.
can it not be on the exam? We just take it off.
I promise you that exact question will not be on the exam.
Oh, cool. Great.
Yeah, I told you guys the format's like 5 questions, you choose 4. That's out there in the world, right?
Is that how the exam's gonna be?
Yeah, there's 5 questions,
Yeah,
you
I don't
pick
think
4.
so. I don't think you told us that yet.
Oh, okay. Oh, I didn't know that. That's great.
Yeah. 5 questions, you pick 4. Some people like that, some people hate that because, you know, they get like analysis paralysis and don't know which one they want to do. But maybe if you're decisive, you can say, oh, I definitely know I don't want to do that one. So maybe that could be helpful. All right. So here we have some bolt connecting 2 components together. The bolt's 60 millimeters in diameter, or sort of approximated by a, you know, a solid tube of 60 millimeters in diameter. And this sort of nut is being tightened. All right. The modulus of the bolt 200 GPa, Poisson's ratio 0.3. Determine the internal force in the bolt. The diameter decreases by 13 micrometers. Okay, so this is when you see problems like this, where it's like one of the lateral dimensions is changing, like it just needs to scream like Poisson's ratio to you or something associated with Poisson's ratio. Okay. So that's where your mind should kind of like immediately go. All right. And, you know, in this portion of the class, we have like a couple of key equations. It's Poisson's ratio is negative lateral over axial. We have things like the modulus is the load divided by the strain. You have things like stress is load divided by area. So when you see problems like this, you're probably going to be thinking about like, all right, I got to maybe use these in some sort of combination to sort of link things up and get me to where I need to go, right? And that's more or less what we're doing here. It's testing your flexibility with how comfortable are you like maneuvering these equations and getting them to give you the answer that you need for something like this, okay? So, you know, I particularly like questions like these because they're not like super straight ahead. It kind of forces you to make some links between like what you're given and what you want. And it takes a little bit of flexibility and plasticity in your brain. So I kind of like questions that look like this. But okay, so we know that we have a diameter change. That should scream to you lateral strain, okay? So wonderful. Lateral strain. This is the change in the diameter over the original diameter, right? So here we have negative 13 micrometers over the original diameter, which is 60 millimeters, right? So that's going to give you some lateral strain, all right? I don't actually have that number on my solution. Looks like it's maybe going to be like 0.25, something like that. 250 microstrain, something like that. Approximately 250 microstrain, something like that. All right, great. But really, we want to end up using Poisson's ratio to get us to an axial strain. Then that axial strain can be used to sort of get us to the axial stress using the modulus information that we have. And then that axial stress can be related back to the load when you have the cross-sectional area of the bolt. All right, so that's kind of the general purpose. So I want to get to the axial strain, which looks like the negative lateral strain over Poisson's ratio. It's just this equation up here, which has been rearranged for the axial strain. So here we just saw this. This is negative 13 micrometers over 60 millimeters divided by the Poisson's ratio of 0.3. In this number, I do have 722 microstrain. All right. And remember what microstrain is. It is 722 times 10 to the negative 6th strain, which is just unitless. Okay, so don't forget about what that microstrain unit is. Sort of a very unique thing that pops up in mechanics of materials and structural analysis. So make sure you're comfortable with that particular special unit. Won't really see that in any other class. Okay, once you have this axial strain, 722 microstrain, now you want to get to your axial stress, which is simply the modulus times the axial strain. So here, our elastic modulus given 200 GPa multiplied by your axial strain. And so we're going to get axial stress in this particular case, 144.4 MPa. Okay. Finally, once you have your axial strain, you can use that to calculate the load. Which is what it's sort of asking for in the problem. What's the internal load inside of this particular material? Can rearrange this guy for load if that's what you're after, which is the axial stress multiplied by the cross-sectional area. You can use the reduced area if you want. You know, the area has been reduced slightly because the diameter changed from 60 millimeters to a slightly smaller diameter, but that's going to be within the noise. So I'm just going to stick to the original cross-sectional diameter. So we know this is 144 ME2004 MPa multiplied by the cross-sectional area. This is pi times the radius squared. We were told this originally 60 millimeters, so the radius is 0.03 meters squared. And this gives us an internal load or an axial load here of 408 kilonewtons. How do you feel about that, Kyle?
Pretty good.
Good.
I didn't know we are supposed to use that ratio for Poisson's ratio.
Poisson.
The lateral over longitudinal, but I got it now.
Yeah. Yeah, it's kind of, we did something pretty similar to this in homework 4. You did, with that volume change problem, you're using like axial versus transverse dimensions to calculate volume change, things like that. So got to be flexible with these sorts of things, understand what Poisson's ratio is. You know, when you pull on something this way, it gets shorter this way. Just be comfortable with those sorts of things. Okay. And you still want to do 11, Kyle?
Yeah, I just don't know how to set it up.
Yeah, this one's a little tricky because you got like this one plate between two rubber pieces. And this is just getting back to the fundamentals of shear strain and shear stress, kind of how we defined like those rhombuses that started this way and then sort of like shifted like this, and how we kind of get those angles and things like that. So let's go ahead and look at number 11. Okay, there's our figure, and I'll just copy the problem statement in here quickly. Two blocks of rubber, each of which 60 millimeters, bonded to rigid supports and a movable plate AB. All right, so here's the movable plate AB. Here's your rigid support, and then you have your two rubber bits here and here. So those rubber bits, these are sort of like the non-rigid mobile rectangular blocks that we're going to kind of like pull against, more or less. All right, we've got this force, 19 kilonewtons. It causes a deflection. So here's our deflection down here in this case of 3 millimeters. We want to find the modulus of rigidity of the rubber. Right? So kind of understand like what's happening here is we're just kind of pushing on this middle plate here, and that's going to cause these internal rubber bits to go from their current like rectangular shape to sort of like this rhombus shape. Something that looks like this and this. So when you see this like deformation that's going to create what looks like rhombuses for you, that just has to like scream to you shear stress, shear strain, something that looks like that, right? Okay, so we want to find modulus of rigidity, which is typically given by the variable capital G, right? And really the only equation in this class that we've seen so far that uses that modulus of rigidity is the shear strain, the shear stress is equal to that shear modulus times the shear strain gamma. So we probably need to do some work finding shear stress, probably need to do some work finding the shear strain. Once we have those two bits of information, G should pop out for us, right? So let's sort of think about each of these two different things separately and how we're going to attack this. So quickly, I'll look at more or less what the free body diagram is of the plate by looking at it from the side view, right? FBD of plate B, and this is side view. So the idea here is, okay, I got this plate here. And this is the plate B, and I'm pushing on it with this force P over here, P. Okay, wonderful. In order to balance that load P, those rubber bricks on the top and the bottom must be providing some shear force equal and opposite, which is P over 2. Okay, each one of those rubber pieces has that load P over 2 kind of providing resistance to the force P that you're sort of pressing this plate into that assembly with. Hopefully that's clear. Okay, so that's of the plate B. I also probably want to do a free body diagram of one of those rubber bits. So let's look at one of those rubber pieces. And let's just, look at this one here on the bottom. Well, I'm originally going to look something like this, and this is going to be fixed into the rigid support at the bottom. We're told that this is sort of fixed into the bottom. And, the plate is pushing on, being pushed on with a value of P, and the rubber is resisting this direction with P over 2 according to the plate. So that means that the rubber is experiencing, by equal and opposite forces, P on 2 in this general direction. All right. When it gets pushed at the top with that force of P over 2, it's going to cause this rubber to kind of turn into this like rhombus shape. Kind of already sort of shown and talked about. And when you see this rhombus shape, again, it should just scream to you shear strain. Okay? And what I mean by shear strain is that we know that the definition of the shear strain that we talked about in class is this angle that forms when you have this sort of like rhombus developing. So this is the shear strain angle gamma. And you could calculate this yourself, but we know that tangent of gamma, in this case, is going to look something like this dimension here, which in this particular problem is sort of running out of room here. This is the dimension delta. We're told what that is, 3 millimeters. So this is going to look something like delta over the original height of the piece. Where the height in this case is 35 millimeters. So let's call this H height. All right, we're told that that delta is 3 millimeters. H is 35 millimeters. And so you could run this, find that gamma is the tangent inverse of this thing, or if you just want to take it straight as it is, because we're assuming small angle, you could do that. But here, I'm going to just calculate directly, 0.0855 radians. So this is step number 1, is finding the shear strain. This is one portion of the Hooke's law that you need to do this calculation. So we just found that guy there. This is what we're looking for. And now we need to work on the shear stress tau, right? So gamma, 0.085 radians. Now the question is, what about the shear stress? Well, we know shear stress is going to be something like load divided by cross-sectional area. Okay? Wonderful. Then the question is, what force and what cross-sectional area do we use in this case? All right, let's go back to our example with the rubber here, okay? So here, we've got this load that's a load of P on 2, okay? We actually know what this is. So the force is P on 2, and we're actually given in the problem that that force that's applied is 19 kilonewtons. So we know what this value is already. This value P is 19, so the force that's going to be applied is 9.5 kilonewtons. Okay, fine. But the harder, trickier bit about this is what is the actual area that we use in the calculation of the shear stress? And for this, you really want to get back to the fundamentals of mechanics about the shear stress. What direction is the stress and what face is it acting upon? Well, in this case, the shear stress has some directionality associated with it, which is like the left direction, okay? And then what face is that shear stress acting upon? Well, that shear stress is acting upon the top face of this rubber bit that's like in contact with the plate. So if we go back up to that image up here and think about like what area is this acting upon to create that rhombus, it's like the area here on the top face of this rubber bit, okay? So that's the area upon which like this P on 2 is acting over the top of this rubber piece. So this here is really the area of interest to us that we want to use in our calculation of the shear stress, right? What face is it acting on and what is the direction of loading? Well, in this case, the face that it's acting on is this face and the direction of loading is towards point A there. Okay, so the area that we want to use here is this area here, which looks something like W, which we're given in the problem is 60 millimeters, by this 180 millimeters here. Right. So here, the cross-sectional area, this is 180 millimeters, or what I'll say is 0.18 meters, times the width, 0.06 meters. This load here is 19/2 for reference. All right, so punch all this in, you'll get a shear stress that's acting on this particular guy, 880 kPa. We're not quite done yet. We just have to finally calculate that shear stress value, or sorry, the modulus rigidity, or modulus of rigidity G is tau over gamma. So here, 880 kPa over 0.0855 radians, or strain, sort of unitless in this case. You'll get a modulus here, 10.3 NPa. And that's your answer. I do have a question. Oh, no, we do not have a question. That must be something else. Okay. Any questions on this problem? Or any
Looks
other?
Fantastic.
Good. Any other problems struggling with? Maybe just want to talk about how to tackle it?
Can we talk about 9?
Let's talk about 9. Yeah. 9 is very similar to problem number 4 from the most recent homework. Maybe let's just talk about how to attack it. Maybe we don't have to go through the whole thing.
Sure.
So here's your image. I'll bring in the problem statement. Black shown, negative magnesium alloy, modulus 45 GPa, Poisson's ratio 0.35. Compressive stress of sigma x, here my subscript got a little mixed up, negative 180 MPa. Okay, so we have compressive stress, compressing or squishing this thing, so that's why we have a negative sign. Determine the magnitude of sigma y, so the stress in the y direction required to keep the height of the block exactly 40 millimeters. Okay, so we had a problem that was similar to this. Maybe you remember the plate problem from the homework, where you kind of had something pulling like this, you had some sigma x, and then you had some sigma y, kind of going like this. And then the question was, what sigma z so that T does not change? Where T is the thickness of the plate, all right? When you see multi-axial loading, what I mean by that is some stress in X, some stress in Y, both together acting, you should be thinking of your generalized 3 Hooke's law. So I'll pull up your equation sheet here really quick just to remind you what that looks like. But on your equation sheet, we did derive all the equations for like generalized Hooke's law. So I'll just pull this in here really quick so you see what this looks like. But these are your general Hooke's law equations. strain in terms of stress, stress in terms of strain. And when you have multi-axial loading, things that it would involve both like a sigma y and a sigma x, you're probably going to want to be thinking about these types of equations. All right. So in this case, we have a situation where we're asked to keep the 40 millimeter dimension consistent. So if we go back to our figure here, we have this y dimension, this x dimension, and this z dimension. All right. We can see from the figure that there is no sigma z. So in this case, sigma z is 0. It's kind of giving that to us straight away. And then it's asking, determine the magnitude required to keep the height of the block exactly 40 millimeters. So what does that mean the strain should be if the dimension is not changing?
0.
Yeah, exactly. So in this case, we want the strain to be 0. And which strain do we want to be 0, Yusa?
The strain acting in the y direction.
Yep. Because that'll just lengthen y 40 millimeters. Okay, so that's all there really is to it. Once you know that you need that epsilon y to be consistent, and you're given a series of stresses and asked about the stresses, then it's like pretty straight ahead at that particular moment. So you'll use that equation, which looks something like nu sigma x on E plus sigma y on E minus nu sigma z on E as your base. You know you want this to be 0. The stress in Z is given as 0. There is no stress acting on the space. We can sort of see that from the image in the problem. And so all you're really left with is some equation that looks like nu sigma x on E is equal to sigma y on E. These e's are going to actually just cancel themselves out. So you have just nu sigma x equals sigma y. You're given sigma x, you're given Poisson's ratio, so you can just calculate this guy directly. Clear?
Yes, thank you.
Alrighty.
Yeah, that's all the questions that I had.
Cool. All right. What about an hour, 20 minutes?
Ooh,
So
I have
we'll-
one more question.
Okay, yeah, go ahead.
It's not on any of the questions that are in the exam review, but is there a potential of us getting a stress cube or a shear cube, like the unit cube on the
Yeah,
exam?
possibly, but it will be pretty straight ahead if it is. You know, similar to like the homework problems. Like there's a homework problem where I just kind of said, all right, here's the situation, draw the stress cube. You know, you might have to do some, all right, what's the force over the area, and then just put it on the cube. It's not going to be, it shouldn't be too complex.
Okay. All right, thank you.
Are there any questions we should focus on? Should focus on all of them, Michael. Quit fishing.
Professor,
What's up?
have a good night. Thanks for doing this for us.
Oh yeah, you're welcome. See you tomorrow. Get ready to
Yep,
dominate.
bye.
Okay, see you guys.
Thank you, Professor.